Yes, hi everyone. First I want to thank the organizers for giving me the chance to present some of the work that I've been doing together with Daniel Schmidt and Laura Segunsky, both from Frankfurt University, and also this project is embedded in a larger project that is also in collaboration with these people listed down here. So today I want to present you some theory work about Scalar-Tensor theory. The people before me already did a nice introduction to Scalar-Tensor theory, so I think I'm just going to skip this slide. The important thing to just keep in mind is that the scalar part here means that we have an additional force which is being mediated between objects. All right, so what is the situation that we are interested in about? It's the in-spiral phase of binary systems. During the in-spiral phase, if you want to calculate the gravitational radiation, then you are quite in luck because you have three scales that are clearly separated. One scale, for example, is the size that your objects have. Here denoted by capital R, then you have the orbital scale, lowercase r, and also the scale of the wavelength of your gravitational radiation, denoted by lambda here. And as I said, during the in-spiral, these scales are clearly separated, which makes calculations a lot easier for us because this means we can construct an EFT to arrive at a relatively easy formalism to calculate the gravitational waves. The pipeline, if you want to do something like this, would be somewhat like this, that you start with your full theory, so these would be the Einstein equations here. Then first you would integrate out, so to say, the scale of the size of your objects to arrive at an effective word-line action. You can essentially think about this as describing your objects as point-like particles. Then you would tailor your effective field theory now to the binary system, and finally you would integrate out the orbital scale to arrive at a theory that describes the radiation. So, and this is nothing new. This is something that was already presented almost 20 years ago by Goldberg and Rothstein. What we've been doing now is to adapt this formalism to Scalar-Tensor theory to then calculate what the radiation looks like if you have this modification to GR. So just to give you a little bit of a teaser how this looks like in practice, what you would do is in vanilla GR to just take your Einstein-Hilbert action, expand it around flat space, then you would get this expansion here where H denotes the metric perturbations. You have a quadratic term, a quartic term, a cubic term, and a quadratic term, and so on. You do the same thing for your point particle action here, where you get then also this nice expansion. Now, if you look at this, then this already looks almost like just a quantum field theory on a flat background. So why not also treat it as such? So from this quadratic term here, we would get something like a graviton propagator. From the cubic term, we get something like this three-point interaction and so on. And likewise down here, you would get these couplings of the word line of your particle to gravitons. And a small disclaimer now, even though I'm talking about gravitons and so on, I'm not actually doing any quantum physics here. You can essentially think about this as doing as evaluating the path integral, but only on the classical level. So I'm not taking into account any quantum loops. So now what did we do? We added this additional scalar field. If you think about this now in terms of the effective field theory, then what you should do when building up your point particle action is to take into account all possible operators that respect the symmetries that you want to have in your system. So of course we would like to have the pheomorphism invariance. Then the leading order operator that you could possibly think about is to just directly couple your scalar field to the word line of your particles. But you don't have to stop there. So you can also encapsulate even more complicated operators. So for example, just phi squared coupled to the word line and so on. Likewise, we have to supplement the action for the scalar field itself. So here we have just the kinetic term, some mass term, and then also some higher order interactions. Now, if you do this expansion and so on, you collect all the Feynman diagrams, then you arrive at something like this. So these would be almost all the diagrams that are relevant at the next leading order. You would have to calculate these diagrams, which means you have to calculate a lot of integrals, but I will spare you from this and just show you some results instead. So what I'm showing you here is the relative power loss at certain Pn orders relative to the quadrupolar emission, which is the leading order. Here I'm so far showing you the vanilla GR emissions, so the 1pn corrections, the 2pn and 3pn corrections, which are just straight lines in this plot. So this is a log-log plot. On the x-axis you have the orbital frequency, and on the y-axis this relative power loss. These are straight lines because in GR you just have that these corrections are some power of the orbital frequency. Now if you add your scalar field, Then at -1 pn order, so this is dipole radiation, you see this sort of shape for the power loss. What is notable here, it's not exactly a straight line. Instead, it falls off identically to 0 at a certain frequency. This frequency here corresponds to the mass of your scalar field. So essentially, you can only radiate dipole emission if your outer frequency is at least the mass of your scalar field. But you don't only have dipole emission, you also have quadrupole emission, for example, which is denoted here by the 0 pn order. Notably here, it drops off at 0 at half your scalar mass. And then you also have some even higher order corrections. So what I denote here by 0 pn mod, this is the corrections to the quadrupolar emission due to the presence of your scalar field. So your scalar field does not only modify the power loss by being radiated itself, but it also modifies the binding energy, for example, for your system. So this means you get different, at a certain orbital separation, you get different orbital frequencies. So we are currently finishing up the calculations for the waveform. We are thinking of hopefully publishing in June. At that point, you can then basically take your favorite scalar-tensor theory. You only have to figure out what is the scalar charge, for example, what is your scalar mass, and you can directly obtain then the waveform, the gravitation waveform, and also the scalar waveform and so on for your favorite model. And with this, I want to conclude and say thank you.
Thank you very much. Other questions for our speaker? Yes.
Are you planning to go to higher order, like calculate the loop corrections?
So for the loop corrections, in general, you can compare those to the tree-level corrections. Then you will typically see that the loop corrections are suppressed by powers of h over the angular momentum of the system. And that's a pretty small number, so you don't expect the loop corrections to have really a noticeable impact. For the higher orders, so far we've calculated the next to leading order corrections. It would definitely also be interesting to go to, like, for example, let's say 2 pn, because then you can encapsulate even more parameters of your scalar-tensor theory. These calculations are going to be much, much more difficult. We're currently working on trying to optimize the pipeline to make it more easily accessible, but like definitely, like especially like in the future when we have high precision measurements, it would be interesting to go to higher orders, because then you are in a position where you can really distinguish better between different modified gravity scenarios. Because if you just consider leading order, you just have the scalar charge, and the scalar charge is something that is really generic to modified gravity models, so you can't really distinguish well between different models.
Thank you. More questions for our speaker? If this is not the case, there is one. Okay, sorry, I overlooked you.
Hi. Have you thought about the impact of the mass on the sort of the propagation of your gravitational wave? Because you're talking about waveforms. Do you mean the tensor waveforms or also the scalar waveforms?
So yes, the tensor waveforms and also the scalar waveforms. I mean, I think you mean the impact on the tensor waveforms, or?
Well, actually, I was thinking of the scalar. So if you have this scalar has a mass, I guess it will kind of dissipate. I mean, it will kind of spread out, right? So the emission that you get at the source will not be the sort of the waveform that you get at the detector.
Yes.
But yeah. I think your tensor waveform should propagate as normal. And
right.
Be fine. Yeah.
Yeah, exactly. We've also been thinking about the scalar waveform. It does definitely dissipate faster due to the mass term. Also, what you have is, so when you calculate actually the power loss, what I showed you was the result for these leading order sort of topologies here. However, you also have these tail effects, which I think maybe is what you're also thinking about. These would be encoded in these topologies down here. So, for example, you emit some scalar radiation, and then it back reacts with the potential, either the gravitational or the scalar potential of your binary, and then thus changes the waveform. These effects are, however, at a higher PN order. So I think, for example, this diagram here would start contributing at the 0.5 PN order. So we haven't calculated it yet, but it's also definitely something on the plan for the future.
Okay, thanks.
Further questions? If there are none, let's thank our speaker again.